Okay, it's a great pleasure to to introduce Matthew Lorentz from Michigan State University. His title is Hochschild Cohomology of Uniform Roe Algebras. So Matthew is our last speaker this afternoon. Matthew, please.
Thank you, and thanks for the introduction. And I'd like to thank the organizers for inviting me today. It's a great privilege to speak here. Even though I was 7 when Cyclic Cohomology was born, I just received my PhD this last spring. So academically, I'm still young. Okay, so to start off with, our goal in this talk is to show this theorem, that if every element of the nth dimensional continuous Hochschild cohomology of the uniform row algebra admits a weakly continuous representation, then that nth dimensional continuous Hochschild cohomology vanishes. And to start off with, I'm going to recall a whole bunch of things that are probably pretty obvious to most people here, but just to introduce you to my notation. We'll start off with them. So bounded geometry, this basically says that if we take a ball of radius r and we put it anywhere in our space, we'll have at most nr elements in that ball. So a couple of examples of this are the integers with the Euclidean metric. It's got very bounded geometry. We can say exactly how many elements will be in a ball of radius r. But we could also maybe look at a finitely generated group, endowing that group with the word metric. It's not hard to see that that will also have bounded geometry. And in this talk, we're going to assume that all of our metric spaces have bounded geometry. And then the uniform row algebra, these have been talked about a little bit in this conference, but let me just redefine them here. So we start with a metric space, X, and then we take an operator T in the bounded operators on the square summable sequences. And we say that that operator has propagation at most R if its matrix entries, this T sub XY there, which is taking the inner product against the canonical basis. If that's 0, whenever the distance between X and Y is greater than R, for all of the X, Ys and X cross X, we would say that that operator has propagation at most R. And then the set of all operators with propagation at most R, I'm going to use this notation to denote them. The algebraic uniform row algebra is just all of the operators that have propagation less than infinity, finite propagation operators. And then the uniform row algebra is taking the norm closure of the algebraic uniform row algebra, using the inherited norm from the bounded operators on square summable sequences.
Sorry, a stupid question. X is assumed to be countable?
Yes, with bounded geometry, X ends up being countable. Yes. Okay. Yes. This can be done in other situations, but then the notation gets very confusing very fast. So we're sticking to bounded geometry today to keep the notation simple. Okay, so some examples of uniform row algebra. We could look at the uniform row algebra over the integers. And the way I like to envision these are as huge infinite matrices. So if we take a copy of Z going that way, another copy of Z going this way, we imagine this as a matrix, and then a finite propagation operator, an operator with propagation at most R, will have zeros off of a band around the diagonal that has distance R from the center there. So wherever we go off if we go R off the diagonal, all the entries become 0. Another way we can look at these are as a cross product. If we have a group, then we can look at the uniform row algebra as being the cross product of L infinity of the group with the group itself. And basically L infinity, we look at those as diagonal operators. And then the group acts on that by shifting the diagonal either up or down. And then we take all of the linear combinations of those. We get the finite propagation operators. And then the norm completion gives us the uniform row algebra. Okay. So next, we're going to have multilinear maps. And it is important to this theory that the C-star algebras that we look at be concrete, which the uniform row algebra is a concrete C-star algebra. But we start with a concrete C-star algebra, and then we let this V here be a dual Banach A bimodule. So as a dual Banach A bimodule, it has a pre-dual. So we can look at things such as the weak star topology on it. And we define the zero-dimensional multilinear maps as just being this bimodule V. And then when n is greater than or equal to 1, these are going to be the maps from the n-fold Cartesian product of A into the bimodule that are separately continuous multilinear maps. And then when we use the subscript W instead of C, we mean the vector space of ultra-weak to weak star continuous multilinear maps. Most of the work we're going to be doing is going to be on bounded sets. So all of the different weak topologies correspond because we'll be on norm bounded sets. So don't pay too much attention to that. And additionally, if we consider A as a bimodule over itself, and this is a little bit tricky, but all of these topologies are going to be inherited from the bounded operator space that they're sitting inside of. So we don't have to worry about what kind of representation we're taking. Okay. And so in that case, we'll just write ln of A, where either subscript may be attached. And then I'm sure we're all familiar with co-boundary operators, but just to say it out loud, our co-boundary operator, we're going up a dimension here. So what this does is we take in a n multilinear map, we give it n plus 1, an n plus 1 vector. And then what we do is we let the first entry pop out, then we take the alternating sum, putting the j and j plus 1 coordinates together. And then finally, we just let the last coordinate pop out the other side there. And that's why it was important for V to be a bimodule. And then for n equals 0, well, the maps in there are just elements of V, right? So if we take the boundary of V, well, this is just the commutator against V. And then, of course, a straightforward calculation shows that this boundary applied twice is always 0. And so the Hochschild cohomology, in our case, we form it just like we would any other ones. We take the co-cycles and we mod out by the co-boundaries. So we take the kernel of the forward map, mod out by the image of the previous map. Okay. So now we're going to be working a lot with multimodular maps. And by multimodular maps, I mean, and we're going to use this notation to indicate the multimodular maps. And by that, I mean, if we have a C-star subalgebra of A, say B, and we take an element B in B, if B is sitting right there, it can just jump out front. If B is sitting against a comma, well, then it can jump over the comma into the next coordinate. And then finally, if it's sitting at the very end, well, it can just jump out the other side. And using the same construction as before, we can form its Hochschild cohomology also. And now for some background. These are some rather old results, but not too old. And just for notational simplicity throughout, I'm going to let A be the uniform row algebra. I'm going to let B be the bounded operators on square summable sequences. and I'm going to let little l be L infinity of x. And to prove our theorem, we're going to follow very closely methods introduced by Johnson, Cattison, and Ringrose. But the way I encountered them was in Sinclair and Smith's book, The Hochschild Cohomology of Uniform Roe Algebras. And since this book helped me understand the theory so much, I felt like I had to plug it. It's a very good book. But through a series of papers, Johnson, Cattison, and Ringrose showed that the continuous Hochschild cohomology of the L infinity multimodular maps that land in the bounded operators on square summable sequences are isomorphic to the continuous Hochschild cohomology from the uniform row algebra to the bounded operators on square summable sequences, which in turn is isomorphic to the Hochschild cohomology of the bounded operators on square summable sequences to themselves. And then they showed that those vanish everywhere. And what they showed was actually much stronger. They showed this for any hyperfinite von Neumann algebra. So it's actually a much stronger theorem than I'm presenting here, but this is all we need for what I'm doing. Okay. So the trick that they use is they start with the inclusion map coming from the L infinity multimodular maps just to the regular maps. And that will induce a homomorphism from the Hochschild cohomology of the multimodular maps to the maps that aren't, well, that could or could not be L infinity multimodular. And then to show that that map is surjective, which is really the key part we're going to need today, is they build this map Kn. And what this map Kn does is it brings it down a dimension and brings it from n down to n minus 1. And then if we take a cocycle, say phi, and we subtract off this coboundary from it, that makes this map L infinity multimodular. So that's how they're getting a surjection on that map. So in order to build this map Kn, it's a very complicated map. But first, we'll let this curly U be the unitary subgroup of L infinity of x. And we're going to let mu be an invariant mean obtained by the amenability of U. And then we take this mu and we can upgrade it to a bounded linear functional on the trace class operators. Since the trace class operators are the pre-dual of the bounded operators on square summable sequences, we end up with an element in the bounded operators on square summable sequences that I'm going to denote like this. So we have a map from the bounded operators from the unitary group to the bounded operators on square summable sequences. So we take these maps and we can map them over to the bounded operators on square summable sequences by sending this A to the element defined by the linear functional that mu has been upgraded to. And this map is going to be contractive, linear, invariant, and it's going to act as the identity on constant functions. So in many ways, this is acting like an integral, and hence the notation. The one thing that we are losing is countable additivity, so care needs to be taken with that. And moreover, we can take any element in the bounded operators, and it can jump in to what I'm calling the averaging operator, and it can also jump back out of this averaging operator. Now the map Kn is constructed inductively. So we start with this map J1, and what this, if we apply it to say psi, we give it n-1 coordinates. And what this does is it puts it into this averaging operator where it puts a u in the first coordinate and it puts the u star out front. And then we build this map G sub k. And what this does, again, it takes in n-1 coordinates and it puts a u star after the ak coordinate in the same coordinate entry, and it puts the u and the k plus 1 coordinate and then lines up the rest afterwards. And then jk plus 1 is going to be jk plus or minus gk applied to the identity minus the boundary of jk. So as we see, this map is very complicated. Yeah, and of course, we let kn be jn. And this map is rather complicated. But it does what we need it to do. So we recall that we know that the Hochschild cohomology of the L-infinity multimodular maps, that vanishes. So using the L-infinity multimodularity, and specifically just using projections in L-infinity, we can show that these maps that land in the bounded operators on square summable sequences that are L-infinity multimodular, in fact, have to land back in the uniform row algebra. They have no other choice because we can move those projections around using multimodularity. So that this inclusion map now from the L-infinity multimodular maps to the maps that go from the uniform row algebra to itself, this inclusion will induce a homomorphism between their Hochschild cohomologies. Now, and I point out that this is not yet surjective. The obstacle here is we would like to apply the same trick that Johnson, Caddison, and Ringrose used. However, you know, we modify a map phi by this map kn, right? So we get the appropriate thing. However, even though this element will be in the correct space, this might not be a co-boundary in there because a priori, this kn of phi lives in the maps that land back in the bounded operators on square summable sequences. So this might not be in the right place for this and this to be equivalent to each other. So in order to correct this, we start using properties of the uniform row algebra. So starting off with, we have this definition of epsilon r approximation. So we start with a metric space. Given epsilon greater than 0 and r greater than 0, we say that an operator t in the square summable sequences can be epsilon r approximated if there's exists an s of propagation at most r, such that t and s are epsilon away from each other. And then we note that if t can be epsilon r approximated for all epsilon greater than 0, then it is in the uniform row algebra. Next, we're going to need a definition and then a generalization of a lemma due to Braga and Farah from their paper on the rigidity of uniform row algebras. And this is a very nice result. To state it, we're going to let blackboard D be the closed unit disk. And for a set I sub k, we're going to let di sub k denote the usual product spaces of functions from ik to the disk. We write the elements of dik as tuples here, which is going to represent a whole series, a very large tuple, because these IKs will be countable. Okay, so now we have a definition, separately symmetrically summable. And I have to give my advisor, Rufus Willett, credit for this. He coined the term. So I don't know where he got it from. but okay. So for a finite sequence of countable index sets, a uniformly bounded family of operators, which I'm denoting as such, that are contained in the uniform row algebra, we're going to say that this is n separately symmetrically summable if the following condition holds. If we just take a random k in between 1 and n, and then we fix all the tuples except for k, then this sum, the partial sums of this will converge in the weak operator topology to an element that is in the uniform row algebra. Then we would say it is n symmetrically summable, separately symmetrically summable. Okay, and here comes the theorem. This is a generalization of Braga and Farah's lemma. And so we have this family of operators that are n symmetrically summable sitting inside of the uniform row algebra. Then for any epsilon greater than 0, there exists an r greater than 0, such that for all of these tuples, the operator corresponding to a tuple is epsilon r approximated. Now, really the significance here is the order of the quantifiers. Saying that they all end up in the uniform row algebra is saying that this r depends on these. But the conclusion of this is saying that there's a single r for all of these. And the way that this gets proven is it's done by induction. So we start with the base case of Braga and Farah's lemma, which they proved. And then we work our way up. And then when we get to the n-1 case, we create these sets U sub epsilon r. And so we take an eta and din, and we say that a sub lambda eta is going to be epsilon approximated for all of the lambdas in the n-1 tuples. That way we can write din as this countable union. Then we suppose that the conclusion of this fails. If the conclusion of that fails, we can then prove that each of these sets are closed and have empty interior, which is a contradiction of the bare category theory. So then this holds. Okay. So we recall our goal that if every element of the continuous Hochschild cohomology of the uniform row algebra admits a weakly continuous representation, then that Hochschild cohomology vanishes. Equivalently, this is the same thing as showing that the map from the weakly continuous Hochschild cohomology of the uniform row algebra to itself to the continuous Hochschild cohomology of the uniform row algebra to itself is a surjection, then it vanishes in that dimension. And what's going on here is we build the homomorphism, this homomorphism from this inclusion, which follows a weakly continuous map is bounded, and therefore it's norm continuous. So we have this inclusion here. It induces this this homomorphism. So if we have a cocycle, we can make it equivalent to something that is weakly continuous. Okay, so I'm just going to give a sketch of the proof because this notation gets out of control really quickly, especially with the complexity of the KN map. So we're just going to show it for a phi in the bilinear maps. And just note that for the higher dimensions, all of the calculations proceed similarly, but they just get really gross really quick. So we start with the K2 map. And by definition, this is J2 minus G1 plus G1 boundary J1. And since all of the terms are in this sum are handled similarly, we're just going to go for the most difficult one. All right. So if we take A in the uniform row algebra, we apply this map to it, we unwind the definition of all of this with the averaging operator, taking boundaries and so on and so forth, and we end up at that. Now, since every term in this sum is handled the exact same way, once more, we're just going to take on this last sum here and try to show that this is in here. Okay. So to do this, we're going to let P sub x be the projection onto the span of the Dirac mass at x. And then for any element f in the unit ball of L infinity of x, we can write f as a weakly convergent sum by choosing the appropriate lambdas. And then moreover, for any lambda in the product space dx, this is going to converge weakly to some element we're going to call G sub lambda in the unit ball of L infinity of x. And now we can assume that phi is weakly continuous. That's the supposition of our theorem. So for any fixed eta in D of x, corresponding to an element G sub eta in the closed unit ball of L infinity of x, this sum is going to converge weakly to this, right? So this x lambda is giving us a f sub lambda in the unit ball. And likewise, any element, this sum on the other coordinate is going to converge weakly to that. So we're two separately symmetrically summable. So this family of operators now is satisfying the conditions of the multilinear version of Braga and Farah's lemma. So for any UV in the unitary group of L infinity of x, since this worked for anything in the unit ball, it's going to work for anything in the unitary group. Given an epsilon greater than 0, we can write this term as A of UV plus B of UV, where A of UV has propagation at most R and B of UV is less than epsilon. Now, if we take a standard matrix unit, E sub yx, and we take the trace of E sub yx against A of UV, we get the matrix entry for A of UV. And since A of UV has propagation at most R, that matrix entry will be 0 whenever the distance between x and y is greater than R. And for all u and v in the unitary group of L infinity of x. And so the linear functional under the hood of this element is going to send that matrix entry to 0 whenever the distance between x and y is greater than R for all of those u and v's in the unitary group. And so that shows that this element here is going to have propagation at most R also, i.e. this averaging operator behaves well with finite propagation. Also, since it's contractive, the B part of this averaging operator will be less than epsilon. And so we've shown that this element is actually landing where we would like it to. And so to conclude the theorem, we have that yes, this is in the correct, this is in here, it always is. But now this part is a co-boundary in the correct space, so that this is now equivalent to this. So this homomorphism we have in between these two, induced by the inclusion map, this will be surjective. And since this space is 0, we're surjecting 0 onto this. This better be 0. Right? Okay. So an immediate consequence of this, and really where this project started, was with derivations. If we look at the boundary of the 0-dimensional maps, that is the space of inner derivations. And if we look at the kernel of the boundary of the linear maps, this is the space of all bounded derivations. And so due to a theorem of Catteson, where he pointed out that all bounded derivations are weakly continuous, from this theorem, it follows that the one-dimensional Hochschild cohomology of the uniform row algebra vanishes, which means that all bounded derivations on uniform row algebras are in fact inner. Okay, so lastly, in the paper that I just recently put up on the archive and is also on my website, explaining all of this, we continue a little bit further to try to explore these weakly continuous maps to try to find a link. I haven't yet, but what we can say is that if the continuous Hochschild cohomology vanishes in all dimensions, then the weakly continuous Hochschild cohomology has to vanish also. And this is coming from a lemma that I prove, where if we have the n-1 dimensional Hochschild cohomology vanishing, then the map from the weak Hochschild cohomology to the continuous Hochschild cohomology is an injection. And if this is 0 and this is an injection, well, then that better be 0. Which I might have had time to go into more detail on that. I realize I've been talking quite quickly. But maybe instead, since I do have a little bit more time. I'm sorry, you're muted.
Yeah, you have a little more time. Yeah, 5-7 minutes. Yeah.
5-7 minutes. Okay, so and I thought I might talk quite a little bit rapidly today, so I prepared a couple extra slides here. So maybe we just talk a little bit about showing how these things are equal. So first we let phi be in the L-infinity multimodular maps. And we take a vector in AN in the product of the uniform row algebra n times. Epsilon between 0 and 1 be given. And we set m to be the max of all of these xi's plus 1. I'm going to add a 1 to it. And note that since each of these xi's are in the uniform row algebra, we can write them as ai plus bi, where ai is in the uniform row algebra, and the norm of bi is less than this minimum. And then, and moreover, we can see that the norm of ai is going to be less than m also. So if the argument of phi has a bk in any coordinate, then we can say that it's going to be bounded by epsilon over n due to this calculation here. And then since phi is multilinear, we can rewrite phi of this vector in x as something containing nothing but finite propagation operators and then everything else has a BK in one of the coordinates. So really, to show that this is going to be in the uniform row algebra, all we have to do is to show that the one containing only finite propagation operators in its entry has propagation at most n times r. So again, we let px be the projection onto the Dirac mass at x, and we're going to let bx of r be the ball around x of radius r, and then this p vx of r is going to be the projection onto all of the elements contained in this ball. So basically, we sum up those projections for each element contained in the ball. And if we have any fixed x and x, if we have px sitting against one of these, we can put a projection of the ball of radius r behind it, because these things have finite propagation, and it's not going to change anything. So these two things are equal. And we can just keep doing this all the way through for each entry. And so what we do is we just pick an arbitrary x, y, such that the distance between x and y is greater than n times r. This will be the matrix entry for the phi of those. And then for any k in this ball, because notice what we do is first, using multimodularity, we bring these projections in, and then we can put this one behind it because it's not going to change anything. Since it's a projection, we square it and then use multimodularity, bring it right over. So we just keep doing that all the way till we get to the last coordinate entry here. And then for any k in this ball, the distance between k and y is now greater than r. So since this entry has propagation at most r, this has to be 0. And then so one of our coordinates is 0 in a multilinear map, means the whole thing is 0. So this matrix entry is 0 whenever the distance between x and y is greater than n times r. This shows that this element lands in finite propagation operators, which is what we needed to show that phi of all of those x's are in the uniform row algebra, because remember, the epsilon was given in the beginning. And that's what I have for you today. Sorry, I was talking a bit fast, but especially at the end of the day, I'm told that a short talk is better than a long talk.
Well, thank you so much, Matthew. Yeah, let's thank Matthew. Okay, so I stopped the recording now.